a new kind of experiment I can show you quickly, and it's one carried out by Rich Hite. I should mention that Wei Wei Wang. Wei Wei Wang is a postdoc carried out almost all of the functional experiments I just talked about. And this experiment that I'll tell you about was carried by Rich Hite, who now runs his own lab at the Memorial Sloan Kettering. And you'll see the question we were after. It involves the experiment was started out with a channel called SLO2, and what you need to know is this is a channel that's activated by sodium. It's a neuronal potassium channel. It's activated by sodium. And the experiment we were interested in is this. So what I'm going to show you here is a set of pictures. So when an electrophysiologist records from a neuron or a cell with channels like this way in it, here's what you see. You see in this recording, this is current on the y-axis, time on the x-axis, and this is a sodium-activated potassium channel. It's in the absence of sodium. In a sodium-activated potassium channel, absence of sodium, you see no channel activity. As you raise the sodium concentration, you start to see with some probability the channel open, and as you raise it further, you see more opening, and in fact you realize that there are at least two channels in that membrane. So what the physiologist sees is fluctuations, the random hopping of the single molecule ion channels, and how you see the stochastic nature of opening and closing. And when we talk about a channel being open, we're not actually we have in mind an open state, but actually the physiologist knows that that means there's some probability it will be opening and conducting. So we talk about open probability, and it looks like this. So you can calculate the open probability and make a graph, sodium concentration, open probability, and it looks like that for this channel. And now the question is, what's going on structurally under here? What do you see? And let's develop this in, and I'll just say that electron microscopy enables this experiment, because in crystallography you couldn't do it. In crystallography you could do the kind of thing I just showed you. You could solve the structure of a channel in the absence of the ligand, you could solve it in the presence of the ligand, and you could check the two combinations, and you could show the kind of movie I showed you of a morph between the open and closed. But what does that mean in terms of the fluctuations, and what does that mean in terms of the number of conformations that might happen in between that closed and open state? So that's what we're after here. In crystallography you couldn't do it because a good crystal requires an identity of what's in the unit cell, which generally implies an identity of structure under a given condition. Whereas in a cryo-EM experiment, you're actually taking your proteins spread out in solution, not touching each other, and in a sense you should be able to get the structure of all the structures that are present in the population of proteins. So in principle you should be able to do a titration of the structure, and that's what we're after here. And so the general strategy is to actually collect data under different concentrations of sodium, and then solve the structures and to do something called classification as what probability are open, what probability are closed, and what we were particularly interested in. How many structures do we see? Do we take intermediate steps on the way between closed and open? So that's what we're after. The way we did it is we combined our data sets, 4 or 5. We couldn't do all 5 because one of them, the 5th one, was collected on a different microscope, and you couldn't combine the data. But we liked the idea of collecting the data sets and throwing them together and processing them together. That way we wouldn't introduce any kind of bias in the way we process them. And then we process them together and classify them and ask, what data set did you come out of? We'll ask that later. First, let me show you a completely open and closed conformation of this channel. So here's the open version. I always show it as blue, and here's the closed version. And this shows the lining of the pore. And you can see there's a big conformational change that I'll show you right here in this movie. So this is again a morph between the closed conformation in the absence of sodium, and then the open conformation in the presence of high sodium. Now this movie did not come from the intermediates. I'm just showing you extremes right now, so you have a sense of what we're looking for. So you see it going back and forth between the closed and the open structure. You can see actually a mechanical expansion of this part in blue that actually opens up the helices that forms the gate of this channel inside the membrane. Those are the endpoints. So back to this titration. So what you do when you classify is you then, first in this case, a little comment about this. In most cryo-EM structures you see, people are often, you'll see this start with a very large number of protein particles called, and then you might notice that the final structure presented represents a small fraction of the total particles, and that's because that small fraction was classified and gave rise to a dense structure. That's perfectly okay to do, but in this case we couldn't do that. We have to keep track of everything. We can't throw things out. The only culling happens here where things in the beginning absolutely will keep the device not particle, and everything else has to be kept because we have to normalize the total number of particles to get these numbers. One little comment that thing we have to be careful in cryo-EM is sometimes I see people referring to a conformation as being significant as a function of the conditions under which it was collected. But if you look and realize that there's only 10 or some small fraction of the total particles, that's not fair, because that was a subpopulation of particles, and you don't know really what the whole population is telling you. So that's something you have to be careful about. So with this classification method, you see in the first concentrations in the 4 data sets here, you can see that in fact if you ask for 10 classes, what you essentially find is one unique class. And the rest are all almost the same. So I'll come back to this. And in the higher concentrations separately, you find again 2 main classes. Well, you get 10 classes, but you compare them, you realize that there are only essentially 2 unique classes in here. So if you now go back and ask for the first 4 data sets, after this classification you ask, okay, where does each class come from? So we ask the 10 classes. I just told you there's only 2 unique ones. But right now let's just keep the 10 separate and say, what happens as a function of sodium concentration? You process them all together, now you just make these graphs. And you say, okay, which particles came out? What's the fraction of class 3? Yeah, 20 millimolar. Class 3 at 40 millimolar, so at 8 and 115. And notice that this class 3 is the only one changing in a significant way. It's well, the rest of them are not doing anything. I mean, of course, as a net, they're dropping a little bit because they're going into class 3. But there's no systematic change of the rate classes. And so what you see is this appearance of class 3. And if you then repeat over and over again, really starting at the beginning to look at the reproducibility or precision of this process, you can see that this is what class 3 does. Class 3 is always, these are 5 independent structure determinations, and you can see class 3 slowly grows as you increase the sodium concentration, whereas as examples, class 1 and 9 do not. Why did I pick 1 and 9? So it turns out class 3 is unique, and the other classes are all not class 3, and they're a little different from each other, only in that there's a rotation of the cytoplasmic domain with respect to the pore. 1 and 9 are both extreme. We can tell the difference between them, and we wanted to know if sodium affected the population, the density of their contribution. And the answer is no. They don't change as a function of sodium. So essentially what is happening here is you make a graph like this, open probability, and now here open probability is actually open probability of the structure. And I've gone back and take out images and put red circles on the closed ones and blue circles on the open ones. And it's not that you can tell from looking at the image that they're open and closed. It's that after determining the structure and classifying, you know every particle that went into every class, and then you can ask what image did that come from, and where were you, and you can now put a color on it. Okay, so the color came from the post-processing, came from the classification. What you can see as sodium is increased, you get So you can see it's a large conformational change. So if something significant was happening in between, we should see. We carried this out with fourfold symmetry, and we also analyzed it without imposing symmetry because we kind of assumed if there were intermediate states, it may be that one subunit goes at a time, but we saw no evidence of that. So it seems that it's, again, a highly cooperative process, and in fact, the Hill coefficient for this is about 3.5, something like that. And the subunits, there are 4 subunits here. And so it looks like as you increase sodium, what you see is you see a population of closed channels, and then a pairs of open channels at some probability that grows as sodium concentration increases. And as hard as we look so far, we do not see intermediate states. So our explanation for this would be that actually, the low energy conformations would be the closed set that are very close to each other, just as rotations of the cytoplasmic domain, and the open state. And all the states, of course, it's not magic, it's of either the closed or the open. So there are relative wells with higher in between, so it spends very little time in between, because essentially what we're trying to do is look at the Boltzmann distribution of structures as a function of sodium concentration. And what we see is only closed and only open, a highly concerted process. And in fact, if you compare the electrophysiology shown here in blue with the cryo-EM that only goes to 300 millimolar, it's kind of surprising how close these curves are to each other, and it's surprising for a few reasons. One is that, somebody might ask about that, what do you think when you freeze? Or when you prepare the Andrews, it's actually evaporation, so do we really have the sodium concentration very well controlled? We don't know, but these are the data. There's one obvious difference. The black curve is clearly going to 1. I think if we went to 600 millimolar sodium, we got close to 1. Here, we clearly are not going to 1. And so there is a discrepancy at the asymptote point of these. And what that discrepancy must mean is that within the set of channels that we define as open, because they've undergone a large combinational change, there are small differences that we don't see that cause them not to conduct. And this is very common. Now, very few channels actually functionally, even if you line the stimulus all the way to open, very few of them go to an open probability of 1. Some do, but many do not. And so this could be as subtle as a blocking ion in the pore that we can't see at the current resolution, or a small kink somewhere, a small conformational difference. To me, it implies there are some states within what we define as open that are subtly different. Some conduct and some do not, that account for this difference. So the summary from this part is that we see an ensemble of closed conformations, and they're sodium independent. They just fluctuate around and don't. The relative populations of what we call closed, the ring channels, do not change. The open conformation emerges in a sodium-dependent manner without stable entity. That is, sodium-dependent gating is highly concerted. And again, as I mentioned, at high resolution, in principle, we should be able to discern differences. And coming back to the question, do I really believe there are absolutely no intermediates? Well, of course, it must be. They're very low populated. And at least in ones that are more highly populated, they're either very close to what we're calling open, and not significantly different from either of those. So we don't discern them. I just want to end with acknowledgement. The sequencing the vacuum channel structure work was carried up on that person. Wei Wang did all the functional data I showed you. Koki Kurihara studies the similar system in the heart. Wei studies the system in the nervous system. But I just talked mostly about Wei's data. And our collaborators, Bruce Dean and Keiko Ware from Harvard, carried out the experiments on dopamine neurons. And the flow to potassium channel titration was carried out by Rich Height. Thanks very much. The sodium titrations are really beautiful. It's amazing to see the sort of structural correlate of the concerted opening. I'm wondering if you were to sort of make a hypothesis as to what an intermediate might look like. As to what? A hypothesis as to what an intermediate might look like. If you were to suggest it had 1 open plus 3 closed, is it possible to make a sort of hypothetical model and then go back to the data set and see if that helps you bring it up? You could do that. So the question is, that's a pretty basic question. Of course, intermediates have to occur because it gets from closed to open. So they do occur, but they're very rare, obviously, because we don't see them. So they're very, underpopulated compared to what we do see because they're at a higher energy level, presumably. And then the question is, what must they look like? So it turns out if you try to open this thing, if you try to open one subunit at a time, you do run into some problems because, in a sense, the way the helices wrap around each other, it's hard to move one without moving all of them. So it seems that if time like yes is, it would have to inch its way out. Not that one subunit can snap all the way, and then a second, and a third, maybe in some order fashion. I think it's got to be a diffusional process where they kind of all open at once because, in a sense, they bump into each other as they open. Thanks. Well, coming back to the gut structure, you have this beautiful high-resolution data. Can you tell us anything about how sodium modulates the ethnicity gamma, and then also understanding mechanism of Weissman's flow channel? Yeah. So the way I think sodium. Sodium is pretty subtle. Sodium is so what I'll say is this. So the answer is I don't really know. But what I do know is sodium. Recall that the cytoplasmic domain rotated and caused a twisting of the helium in direction that kind of opens the helical bundle that makes the gate. Sodium is bound at that interface between the cytoplasmic domain and those helices, and it makes very specific what look like structural interactions. And in my view, sodium tightens up. It basically better transfers the rotation of the cytoplasmic domain to opening of the helices that make the gate. So I think that's what's happening given where it sits. Yes. And then how does that connect to the flow 2? Could the sodium be having a similar effect? And I don't think so. And it's because, as hard as we have looked for where sodium binds in flow 2, we can't see, which is a little bit surprising for the following reason. We've also determined structures at quite good resolution of flow 1 in closed and open conformations. That is a cousin of flow 2, but calcium is the activated ligand instead of sodium. And there we see where calcium binds very clearly. 2 sites per subunit, 8 altogether. If we look at the corresponding sites, we actually see density that we thought was sodium in one of them, what we call the RCK2 site. But when we mutate it to make it go away, we still get sodium activation. So we don't know, and I think sodium works. Notice it was a very low affinity. It takes a lot of sodium open that channel. It takes a lot. So I think it's probably multiple low affinity sites, and it's why we don't see them. But it's working on this gating ring structure that kind of has this very specialized motion that is almost the same as the calcium, the sodium activated one, but it's very different than the rotation that happens in the group. Yeah. Thank you for a wonderful talk.
I was wondering in the third channel when you're referring to TIP2, are you talking about TIP 452 or in any other variant?
I'm talking, so it's a good question. We've looked at a lot of substituted tips, and many of them activate, but it's really interesting because many of them activate with not only different affinities, but different maximum values. It's a whole kind of bunch of data we have not published, but the one that we're talking about here is tip 4.5. But the other tips have interesting effects, and in fact, some are competitive on this one.